In this lesson, we cover a couple of the important features of the SN2 mechanism for nucleophilic substitution reaction. The most important feature is what we in organic chemistry land call backside attack of the nucleophile. Now that usually brings a few jokes in a live class of students, but what do we mean by backside attack? Well, this picture showing you the mechanism should make this clear. In order to, since the nucleophile has to approach and the leaving group has to leave at the same time, the nucleophile has to approach carbon from the side opposite the side that the leaving group is leaving from. So in this case, the leaving group is leaving from the right side of that carbon, and the nucleophile Y has to come in from the left side of the carbon, and that's to avoid a traffic jam. We need to get all the electrons moving smoothly along the highway in the same direction. Notice I said the nucleophile must approach the carbon undergoing substitution and not the entire molecule. Some students make a mistake, and when they're dealing with larger molecules that have to undergo SN2, they try to have the nucleophile attack the left-hand most carbon in the entire molecule. No, the nucleophile has to attack the carbon that contains the leaving group, so be careful about that one. So what are some consequences of backside attack? Well, to start with, the alkyl halide, which is what the molecule undergoing substitution usually is, must be small enough to have enough of an exposed backside to get attacked. So what we say is the alkyl halide must be methyl, primary, or small secondary. This is why we had to learn this in the context of functional groups, why I asked you to learn primary, secondary, and tertiary. If the alkyl halide is not small secondary or smaller, that carbon is going to be too sterically hindered. And one way that's convenient to show this is using space-filling models. Okay, these are models that I could build using a software package known as Chem3D that allows you to visualize what molecules really look like rather than the drawings that we make, the bond line drawings that we make of them. And one of the ways that you can visualize a model in Chem3D is what's called a space-filling model. So each carbon, well, each atom in the structure is approximately the size in a space-filling model that the electron cloud around that atom actually takes up. So on the left side here is a model of a primary alkyl halide, so orange is Br, light blue is hydrogen, gray is carbon, and then the carbon undergoing attack is in dark blue. And as you can see, there is clearly dark blue available on the back side, the side opposite the bromine, for the nucleophile to come in and attack. Contrast that with a tertiary alkyl halide, and you can barely see that dark blue ball at the center. You can see a couple of specks of it, but definitely not big enough for a nucleophile to be able to come in there and get in between the other three methyl groups. Okay, so primary is okay, tertiary is not okay, secondary is kind of the intermediate case. And we're going to see that theme come up a lot in our discussion of nucleophilic substitution reactions. So what I say is an alkyl halide must be small secondary in order for it to undergo the SN2 reaction, so then I should define my terms, right? So my definition of small secondary, not everyone may agree with me, but my definition would be no branching at the beta position. Okay, what's the beta position? The carbon containing the leaving group we call the alpha carbon. Then the next carbon over on either side is the beta carbon. So all four positions, all four substituents at the beta position must, which are indicated in red in this structure, must be hydrogens. Okay, you can still have one group on each of the beta carbons that's longer, but there have to be two hydrogens on each of those carbons to leave enough room for the nucleophile to be able to get in and attack the carbon containing the leaving group. Second consequence of backside attack is one of stereochemistry. So if the carbon undergoing substitution is a stereocenter, the reaction will take place with inversion of configuration. And that is also made clear through this depiction of the mechanism. So in this particular structure, we have 2-bromobutane. That's the smallest alkyl halide that is chiral. However, based on the definition on the previous slide, it's still a small secondary. The methyl group has 3 beta hydrogens. The ethyl group still has 2 beta hydrogens and 1 more carbon. So there are sufficient number of hydrogens at the beta positions. In this case, SH- is coming in as a nucleophile. It is attacking. And in the starting material, the configuration of the 2-bromobutane is S. In the product, the configuration at the stereocenter in the thiol is now R. Okay, so the configuration has switched from S to R. And the way to think about this is that in the reactant, the leaving group is on the right side, and in the product, the nucleophile is on the left side. The other 3 groups on that carbon, the methyl, the ethyl, and the hydrogen, have maintained their relative orientations. We now have the group of highest atomic number. So this is only going to work out switching from S to R when you have the highest atomic number group replacing the highest atomic number group, but that is actually usually the case. That group comes in from the opposite side, so if you make a 3-dimensional model and figure it out, you're going to see that the configuration has switched. Okay, the structure at the center of this scheme is the transition state, the midpoint of the reaction, and also the maximum on the energy diagram. Think back to the lesson on energy diagrams. And what you should note about this is as the nucleophile approaches the backside of the carbon, it pushes those 3 R groups to the right, so that at the transition state, they are all lying in a plane. And then finally, as that SH comes in further, it pushes those 3 groups over to the right to restore tetrahedral geometry in the product. The second consequence of the second major feature, of the SN2 reaction is that since it is a one-step reaction, the nucleophile has to actually push out the leaving group, so to speak. It's not like the leaving group leaves and you have a carbocation sitting there wide open waiting to have the nucleophile come in and attack it. So because the nucleophile has to do more work in this case and push out the leaving group, it must be a very good nucleophile. And in the next lesson, I'm going to look at at the principles of what makes a nucleophile good or not good, and look at some common nucleophiles and assign them grades. That's what professors like me like to do, right? Assign grades. So I'm going to assign those nucleophiles grades, A, B, or C, and only nucleophiles that receive an A or a B are good enough to be nucleophiles in an SN2 reaction.